That's our official start.
Happy welcome back with that. Visiting from MIT via KFTP, and he's going to tell us about conformal manifolds from symmetries and gauging.
Yeah, thank you. So I changed the title of it just to make it shorter. So it's about conformal manifold from symmetries, and this is based on a work to appear. I've been written to appear for quite a long time already, so hopefully it will really appear sometime soon. And then there's a closely related paper which I draw a lot of inspiration from, written by Sergei Dubovsky, Stefan Negro, and Massimo Parati. So that appears in 2023. So I'll explain the relations between my work and your work. Okay, so what is this talk about? So this talk is about my idealized dream is to try to use symmetry to explore the space of CFTs. So that's my idealized dream. So let's first recap how does the space of CFT look like. So in particular, let me just focus on C equals to 1, unitary CFTs for now. So this is has been discussed a lot in the literatures. So at least all the known C equals to 1 unitary CFT we have basically forms this kind of T-shaped regions. So one way to think about this directions is that this is what's called a circle branch. So this is described by a compact boson. Okay. And here phi has 2-pi periodicity. So that since we fix the periodicity of phi, so R parameterizes different conformal field theories. And then in this conventions, we have a T duality that maps R to 1 over R. Okay. So that means that different theories are basically just labeled by half lines, starting from R equals to 1, going to R equals to infinity. So this is what's called the circle branch. And then this thing is what's called the orbifold branch. So this is basically, if you start with compact bosons, then you find that there's a cross conjugation symmetry that maps phi to minus phi. Okay, so what circle branch is doing is basically just orbifold the theories by this Z2 charge conjugations or gauge this Z2 charge conjugations. So this is what's called orbifold branch. And okay. And then on top of that, there are some discrete theories that are called TOI theories. So the way to think about that is the following. So let me say one thing. So this branch and this branch, they actually will intersect at one point, which is at R equals to 2. And at this point, the theory is actually identical to SU2 level 1 WCW models. So in this theory in particular, you see that there's a symmetries that is given by SU2 left and SU2 right, not Z2. Okay. But while on generic points, you just see a U1 symmetry times the U1 symmetries. So the way to understand this U1 symmetry is very simple. So this U1 symmetry is just shifting phi by some constants. And this U1 symmetry is just shifting the U bosons by some constants. Okay. Good. So the way to understand TOI theory is very simple. So there are what's called the E series. They are related to basically just some subgroup, discrete subgroup of SU2, and then you try to gauge that, then you will get a theories that are looking at that give you these 3 theories. So one of them is about gauging A4, the other is gauging S4, the other is gauging S5 subgroup of the SO3. So this is basically most of the C equals to 1 unitary CFTs we know at this moment. Okay, so let me first point out one thing that's important is that here we see that these theories, they are not always discrete. They can be continuously connected to each other by continuous deformation. So for example, this is what happens on the circle branch. So this is an example of what's called conformal manifold. So what is conformal manifold? Oh, sorry, conformal manifold. So what is conformal manifold? So conformal manifolds are basically CFTs that are continuously connected to each other by exactly marginal deformations. Okay, so the way we think about this is that there are some manifolds, and on every point on the manifolds, the theories are some CFTs. And then we can connect them by exactly marginal deformations. So this is exactly what happens in this case, that theories on circle branch can be connected to each other by doing exactly marginal deformations that change the radius. Okay, so and it's the reason and the way to think about it is that we can start with a theory. The Lagrangian of the first theories, we just add some exactly marginal operators to the spectrums, and then this will deform the Lagrangians, and then we can land on the SymTFTs. So in particular, that means that these operators must always have dimension d for d-dimensional CFT. So one thing that's important about conformal manifold is that since this is exactly marginal operators, so the flow is actually reversible. So that means that the central charge on conformal manifolds is preserved. It's the same. Okay. So this is again what happens here. These are all theories that have same central charge equals 1 that are continuously connected to each other, and then the central charge remains the same. So this is a manifold, so that allows us to define a metric, and the metric is naturally defined by the 2-point functions of this exactly marginal operators. So we just take the one exactly marginal operators, and we just compute their 2-point functions. Your 2-point function is given by the metric divided by x to the power d. Okay, and this coefficient is actually meaningful coefficients, and this defines the metric, and this is what's called a homological metric. Okay, so this is a way to think about this conformal manifold, and then it's naturally endowed with the metric. Okay, so my talk today, I'm not going to really use symmetry to solve the space of CFTs. What I'm going to do is I'm going to make a modest step trying to use symmetries to understand this conformal manifolds. So I want to understand why there exists a class of conformal manifolds, and as we'll see that actually the existence of this a large class of conformal manifolds purely just comes from the existence of certain symmetries of some conformal field theories here. And then using this, we'll see that we can make some statements about C equals to 1 theories. Okay. So this is one motivation that I'm interested in understanding the space of conformal field theories, and then I want to, in particular, understand a subset of space of conformal field theories that are continuously connected to each other, and these are what's called conformal manifolds. So this is one motivation. The second motivation of understanding why conformal manifolds are interesting is that they are related to massless fields in quantum gravity. So the connections happens in 2 places. One is in string theory. So in string theory, let's talk about the relations between worldsheet, string theory, and what happens in target space. So we know that given a conformal field theories on the worldsheet, it is related to one solution in the target space, one solution to Einstein equations in the target space. And then exactly marginal operators on the worldsheet correspond to moduli, or sometimes it's just called massless field. It's basically just a massless fields in the target space. Okay, and this actually makes it important to understand this exactly marginal operators, because what's most interesting in the target space is to study the effective field theories of massless fields. And that's why understanding this exactly marginal operators is super important if you want to understand the effective actions in the target space. Okay. And the metric now actually have a natural interpretation. The metric now controls the kinetic terms in the target space that's given by Gij. So here I just say that operators is mapped to some moduli, which is labeled by lambda I. And then Gij, which is the metric, will appear in the kinetic terms. Okay. So this is one place where one place where conformal manifolds appears naturally. It's related to some massless fields in quantum gravity, while worldsheet string theory. There's another place where things happen. It's that about holography. So again, here if you have an exactly marginal operators, they correspond to some massless fields in a target space. So here we see that either through string theory or holography, the exactly marginal operators are tied with some massless fields in the target space or in the bulk, well, ADS-CFT correspondence. So this is actually leads to interesting progress in at least the conjectures coming from swampland programs. So in swampland programs, people are interested in understanding what happens to a modularized space. So suppose you have some string theories, or also well holographies, then you have some exactly marginal operators, and they form they generate some conformal manifolds. Okay, then people are interested in asking what happens if you go to, first of all, people are interested in whether the conformal manifold is compact or non-compact. And the compact and non-compact are defined with respect to this metric, this topological metric. Then the second thing people are interested in is what happens at infinite distance points on this conformal manifold. And there has been some, and this has led to what's called distant conjectures. And if you formulate it or translate it back to conformal field theories, then this leads to what's called a CFT distant conjecture. So this was formulated in 2000 by Permuter, Rastavi, Alpine, and then so okay. So what they're claiming or what they're conjecturing is that if you look at the infinite distance points on this conformal manifold, then things will bifurcate depending on dimensions. So let's first talk about what happens when we have d equals to 2 dimensions. So they're conjecturing that the infinite distance points are related to conformal field theories or directions where the scaling dimensions actually close up. So you have what happens is that you have some operators whose scaling dimension will vanish exponentially fast as we go to infinite distance point. So this is where the scaling dimension vanish exponentially. So this was conjecture. Vanishing, vanish exponentially. And when dimension is greater than 2, what happens is that people conjecture that it's related, not related to the scaling dimension vanishing now, it's relating to the twist dimension, the twist gap vanishing. So twist gap is basically defined by the difference between the dimensions and the spin. And then so it's conjecture that this vanishes. So this was the conjectures, but it turns out that this direction has been proven in the past few years. So this direction has been proven by a nice paper by Hiroshi and Ifan. So by Hiroshi and Ifan Wang in 2000 in last year, and then this direction has been proven by Baum and Caldera Infante also in 23. Okay, so this is the status of this CFD distant conjectures, which is a statement about what happens at the infinite distant points on conformal manifolds. And this direction has been proven, but this direction and this direction still remains as a conjecture. Okay.
This is all operators in the CFT get vanishing scaling dimension?
Oh no, some, just some. Yeah, you just need one operator with vanishing scaling dimensions. Yeah, that's right. And similarly, here's one operator with a vanishing twist gap.
Why is the D bigger than 2 statement non-trivial? I mean,
D greater than 2 statement non-trivial.
this arrow that you drew at the result from 26. The twist gap vanishes, then you have a free theory.
That's right. That's right. So
spin card.
That's right. So
make a list, free scalar or free max or whatever, and then you just analyze that.
Oh, that's right. So vanishing twist gap implies enhanced higher spin symmetries.
Right.
That implies that the theory is free. Yeah, but then you need to show that every infinite distance points are free theories, which actually kind of makes sense.
I thought that arrow you drew is that the twist gap vanishes. It's an infinite distance.
That's right. That's right. Yeah. So you just need to compute this out some large of metric to a point where you have enhanced higher spin symmetries, and then that thing diverges. Does that make sense?
And yes, I just don't understand why it's in, but I thought that was obvious. That was supposed to be a trivial direction that everybody knew about.
I don't know. So
The converse is hard.
Converse is very hard. Converse proving that every infinite distance point is free is very hard. Yeah, but this direction is much easier. I agree. Yeah, this direction is much easier. You just need to check that if you have some emergent higher spin symmetries, then you just compute the metric. Yeah, and then you see that metric should diverge exponentially.
But you just make a list of free theories. That's it.
Maybe I don't understand what you're saying. So
you know what the higher spin theories are.
That's right. That's
They're
right.
free theory.
But then you want to,
Yeah, so then you can compute perturbation theory around the free theory and do the better.
that's correct. Yeah, that's actually what people did. Yeah, that's what people did. Yeah,
Because
that's
it's
right.
ancient, but probably older than you and I.
Oh, okay. So that might be my ignorance. Yeah, yeah. But this I think D equals to 2 statement is more non-trivial, coming from Bootstrap actually.
Yeah.
That's right. Okay. But I just want to mention this because there's some results that concerns about the topology of a conformal manifolds and also what happens at infinite distant points on conformal manifolds. And that's actually motivates some of the things I'm going to say next. Okay, so this is sort of the background materials, and now I'd like to give you the punchline of today's talk, or the summary of the main results. So the summary is that so let's consider 1 plus 1 conformal filter with a U1 times U1 current. Okay, and we'll show that this theories admit an exactly marginal operator. But there's a little caveat is that the operator that we construct might vanish. So we need to check that whether this operator can be trivial, can be a zero operator, can be zero operator. So that's something we need to check. But if this operator is not a zero operator, then that tells you that a 1 plus 1 conformal filter is with U1 times U1 current always live on conformal, I should say like live on conformal manifolds. Okay. That is generated by this exactly marginal operator. And let me emphasize a few points. One point is that here when I write U1 times U1, I'm just talking about Lie algebra. I'm making no assumptions about the global form of the symmetries. Okay. So in particular, the global form of symmetries could be either U1 or R. This is two possible ways to exponentiate a U1 Lie algebra. Okay. So this is one thing. The second thing is that is a bit unusual compared to the usual 2D CFT talk is that I'm not going to assume that enhancement to chiral algebra. So I'm not assuming enhancement to chiral algebra. And we'll see examples where in some cases, in fact, there's no enhancement to chiral algebra. Okay. So that's to make the statements stronger than the usual statements. And in particular, the way I'm going to show the existence of this conformal manifold is by showing that if I start with a conformal filters, if I deform by this exactly marginal operators, the theories living on this conformal manifolds are related to this theories. First, they are related by this exactly marginal deformations. They're also related by procedures called topological gauging. So this is a generalization of discrete gaugings, but now using a continuous group. So this is generalized discrete gauging. I'm going to explain what I mean by topological gauging later. But this is particularly nice in the following sense, because when I do a topological gauging, this is a topological manipulations. And a topological manipulation shouldn't change the central charge. So this guarantees that theories related by topological gaugings have same central charge. And that's consistent with the fact that they are living on the same conformal manifolds. Okay. And this actually have important consequences in the case of C equals to 1. Because in the case of C equals to 1, we know that these theories are related to the SU2 level 1 points by discrete gauging of these groups. But now, knowing that the theories that are related by current deformations are related by topological gauging, then we see that theories on these points are all related by a procedure that is basically topological gauging. Because this deformations is essentially an example of what I'm going to describe here. Yeah. And this also guarantees that orbital branch are also coming from doing some topological gauging of SU2 level 1. Because orbital branch are just gauging charge conjugations on circle branch. So here, this basically tells us that by knowing just the existence of SU2 level 1, we can obtain everything we know in C equals to 1 unitary CFTs by doing a topological gauging. Okay, so that's a consequence of this perspective of understanding this conformal manifolds using topological gaugings. And there are some other consequences I'm going to talk about. Is that we'll see that using this perspective, there's an interesting connection between the topology of the conformal manifolds and the anomaly of the currents. In particular, we're going to see that the topology of this conformal manifold is compact when the two symmetry has no anomaly, and it's not compact when there's an anomaly. Okay, and then we'll also discuss how we can understand this from recent developments of understanding symmetries using a one-dimensional higher topological field theories known as symmetry TFTs. Okay, and lastly, if we have time, I'll discuss how using this perspective we can see some non-invertible symmetries on this conformal manifold, and also construct some hidden boundary conditions. Okay. So, but let me just give you a quick summary of what's happening here. So what's happening here is the following. So let's look at what happens on the circle branch. So on the circle branch, if we're staying away from this point, we only see the U1 times U1 symmetry by our naked eye. But at this point, we see that there's enhanced symmetries, which is given by this SO4 symmetries, which is the SU2 times SU2 minus C2. So usually we would say that the deformations that we do break this SU4 symmetries. But by knowing that points are related by topological gatings, then this tells us that this SO4 symmetry actually is not explicitly broken on the circle branch. What happens is that it actually reorganized. It reorganized into what's called a non-invertible symmetries. Okay, so this is a phenomenon that's generally existing. So if we study continuous deformations coming from the one that I'm going to describe, that on those conformal manifolds, once you have enhanced symmetry points, the enhanced symmetry is not explicitly broken. It just gets reorganized if you do the deformation. Okay. So this is basically the summary of the result.
Is this statement for any central charge that you?
That's right. This statement is true for every central charge.
What's an example that's not the compact boson?
Yeah. So you can start with WZW models, like at some generic K, generic K. And then there's also an example of using non-compact bosons. I'm going to talk about examples that it will be clear. Okay. Now let me describe how what is this exactly marginal operator. So this exactly marginal operator might be familiar to some of the people. This is essentially what's called the current operators. So what I'm going to describe is that once you have the 1 plus 1 CFTs, you can do something called current deformations, and then this will generate the conformal manifold. So what is current deformations? So current deformation is a following idea. So let's now consider conserved currents in 1 plus 1D. Then one can show that using conformal symmetry that this current would have dimension equals to 1. Okay. So then you can try to build a dimension 2 operators by taking a product of two currents. So in particular, I'm going to write an operator that is given by J1 wedge J2. So this is just shorthand for contracting the two currents using epsilon tensor. Okay. And so this operator naturally will have dimension 2. And so this is a marginal operator because each current has dimension 1. Okay. Okay. So
guaranteed this thing doesn't get anomalous dimensions?
Can you say again?
Is it guaranteed that J squared does not get anomalous dimensions?
That's a very, very good question. So I'm coming to that right now. So as Enrico asked, is it guaranteed that this operator will always be exactly marginal? It's possible that after a deformation, it might receive corrections, quantum corrections. So anomalous corrections to its dimensions. So it turns out that one can show that this is guaranteed to be exactly marginal if the two currents J1 and J2 commute. Okay, so let me give you a counterexample why this wouldn't work. So let's consider the case.
Currents or charges?
I think currents. Currents, you can still.
Operators.
Oh, yeah, it's better to say charges. It's better to say charges commute. Yeah, charges commute. Yeah, but yeah.
The same, no singular term in the OP.
That's right. Yeah. So there's a way to understand this if this thing enhances to a chiral algebra. But then there are also examples where this doesn't enhance to chiral algebra. But the key thing is that I just don't want them to have some singular term OP. That's right. That's right. Good. So let me give you another example. So let's say we have SU2 symmetry. Okay. So there's a U1 subgroup that is generated by the sigma X operator, and one is generated by the sigma Y operators. So these two symmetry actually they don't commute. And this is even though they give you two U1 symmetries, but then if you use the occurrence to build an operator like this will not be exactly marginal. Okay. And let me also mention that I make no assumptions about the global form of the symmetry. I'm coming back to this later. No assumptions on whether the symmetry is U1 or R. I'm coming back to this in a moment. Okay. So now let's try to connect this to something that we know before. So let's first consider. Let's first stay in the territory of unitary compact CFTs. Then I'm going to talk about what happens in a unitary non-compact CFTs. So in unitary compact CFTs, it turns out that things are. So let's talk about unitary compact CFT. So compact CFT just means that the operator spectrums are discrete. There's no continuous spectrums. Okay. So in unitary compact CFT, one can show that if you have a conserved current, then its postule is automatically conserved. Okay. So since both the current and its postule are conserved, then you can use them to build a chiral current, which is basically given by Jx minus IJy and plus IJy. Okay. So this are chiral currents that they will obey the chiral current conservation equation. Okay. So then in this case, the operator that I wrote down before just reduces to the familiar JJ bar operators. So you can write it by composing the current J and J bar. Okay. And it has been proven actually in the 80s. It has been proven in the 80s by Chowdhury and Schwartz that this operator is exactly marginal if this condition is satisfied. Okay, if this condition is satisfied. But the way they prove it is the idea is very simple. They actually do sort of a brute force calculation. They just they write down these operators and then just check whether this operator computes its OP against itself and check whether this operator receives anomalous dimensions. And because we know that the symmetry enhanced into chiral algebras, so a lot of OP are just fixed by the chiral algebras. So they can actually derive the conditions I wrote there using by checking explicitly the OP of this operator against itself. Okay. So this is what happens in unitary compact CFTs. And there are examples. So one natural example is given by the Narain CFT, which is basically a bunch of compact bosons. So this example, the way to think about this example is that there are two parameters that parameterizes the moduli space or the space of conformal filters. So one is the metric in the target space, which is given by this. This is the metric. And the other is the B field in the target space. Okay. So this series are parameterized by these two parameters. And the conformal manifolds parameterized by these two parameters can all be generated by just doing current deformations using the currents that is given by partial mu Ji and epsilon mu nu partial mu Ji. Okay. So this is one example, and the other example is the one I mentioned before, that you start with the WCW model. Then you can, let's say for example, SU level K, you can take some U1 from a carton of SUN and use the currents to do a deformations, and then that's also will give you a conformal manifold. So this has been discussed in 2016 by the Forster by Forst and Rogenskin. Okay. So this is what happens in unitary compact CFTs. That everything I said from here can be understood using JJ bar deformations. And the symmetry guarantees to be enhanced into a chiral algebra. But now let's go back to a more unusual territory. That is, let's consider unitary non-compact CFTs now. So we're still staying in the unitary world, but now we consider non-compact CFT now. So non-compact CFT just means that the conformal field theory has a continuous spectrum of operators. Okay. So let's first talk about a non-compact boson. And let's say we set the central charge to be 2. So in this case, we can parameterize the theory by a complex boson. So this is a complex boson. So since it's a compact boson, then one thing we can do is that we can try to rotate this compact boson by a phase. Oh, sorry, the complex boson. Sorry. Yeah. Thanks. Yeah. Thanks. That's important. It's a complex boson. Okay. Yeah. So we can rotate this complex boson by a phase. Okay. So let me emphasize that this is similar. This is different from the symmetries we talk about in the case of compact boson. In the case of compact boson, the symmetry we talk about is just shifting the compact boson by some numbers. But this is rotating the complex boson by some phase. Okay. So this is clearly a symmetry of this theory, but we ask what happens with current. So its currents take the following form. Okay, and so one comment of this current is that this current is neither a primary nor a descendant. Okay, so this is a weird operator. This is clearly a current for the symmetries, but this is a weird operator. It's neither primary or descendant. And in particular, you can compute the 2-point functions of this operator. And this 2-point functions will contain some logarithms of x. So that's why this is a bit of unusual operators. And this operator actually doesn't enhance, this U1 symmetry actually doesn't enhance to a chiral algebra. So we don't get parallel algebras, no parallel algebra. In particular, one can check that the Hodge field of this current is actually not conserved. Okay. But still, you can try to use this current to perform a current deformations. And so that has been discussed in the literature. So let's now consider C equals to 4 non-compact boson. So this series will have 2 complex bosons. I runs from 1, 2, okay? So in this series, we can just take the U1 symmetry that rotates the first compact boson and the U1 symmetry that rotates the second complex boson and use the occurrence to build the current operator I wrote down before, then try to deform the theory, okay? Then you can ask, what do you get? So this is a theory with explicit Lagrangians. So one can write down differential equations and then try to solve it. So first, to describe it, let's just parameterize the theories in polar coordinates. Okay, so let's parameterize the theories in polar coordinates. Then this basically just becomes something like this. I'm just writing things in polar coordinates now. Good. So now one can ask what happens if I do a current deformations. So if I do a current deformations, what happens is that I get a nonlinear sigma models. But this nonlinear sigma models, even though it looks super horrendous or super weird, it's secretly describe a conformal field theories. And let me just show you quickly how the metric and B field look like, just to give you an idea, but the details doesn't matter. So the metric look like the following. So it's I rho 1 squared 1 plus lambda squared rho 1 squared rho 2 squared 1 rho 2 squared 1 plus lambda squared rho 1 squared rho 2 squared. Okay, so this is the first. This is the metric. And what is the B field? So the B field has a bunch of 0. And the non-zero things is it's this one, 1 and minus 1. Okay, so let me just emphasize that this is a 2x2 box. And then this one is sitting here, and this minus 1 is sitting here. And with the coefficient given by lambda, rho 1 squared, rho 2 squared, 1 plus rho 1 squared, 2 squared. Okay. So this is a nonlinear sigma models with both the metric and B field turn on. But then this secretly describe a conformal field theory. If you believe what I said before, that if you start with a conformal field theories with 2 U1 symmetries, then you can generate a new conformal field theories using these topological gaugings. Then this things is essentially what those topological gauging will give you. Okay, this is a nonlinear sigma models that secretly describe a conformal field theories. And in fact, this metric and B field has been discussed before. So this is discussed first by Looney and Maldacena. And the reason why they were interested in this is that they were not interested in conformal field theory to begin with. What they're interested in is that they want to solve with solutions to Einstein equations, and whether they can generate new solutions to Einstein equations. And then what they found is that there is something called TST transformations that would generate a conformal, that would generate new solutions to Einstein equations. So what is TST transformations? The idea is very simple. It's just I'm already write the theories in polar coordinates. So T is basically doing T duality. So it will first do a T duality that maps θ1 to θ1 tilde, which is the dual boson. Then you do a shift, the shift θ2 by the first dual boson. Then you perform a T duality again that maps the dual boson back. Okay, so this thing combines into what's called a TST transformation. So it's T duality, shift, and T duality. And this is a way to generate new solutions to Einstein equations. And then, as we know that the new solution to Einstein equations is supposed to correspond to new CFTs on the worksheet. So that's a way to connect this solution generating techniques proposed by Looney and Maldacena to a concurrent deformations. Okay. So this is just to show you that this concurrent deformations still make sense even in unitary non-compact CFTs where we don't automatically get a chiral algebra. Okay. Is there any questions? Good. Okay. So good. So this is all about concurrent deformations now. So now I would like to convince you how we can think about concurrent deformations using a more topological perspective. And this will automatically explain why concurrent deformations preserve marginality.
And N equals 4, which, well, they did this in ADS5, right? Not just in.
Yeah, they did it in ADS5.
So which marginal deformation of N equals 4 is?
I don't remember now. Sorry.
Oh, beta.
I think it's related to beta deformation. If I remember. Yeah, I need to check. Yeah. Yeah. It's related to one of those deformations. Okay, so now let me try to discuss. Okay, now I would like to convince you that we can think about concurrent deformation using this more topological perspective. But to do that, we first need to formulate concurrent deformations in a more abstract way. So before, all the examples I talk about, like compact boson WCW models or the non-compact boson examples, we all have explicit Lagrangians. So we can write down the currents, we can write down the differential equations to solve the actions. So then we know what is the sigma model we're looking at. But now we like to do things more abstractly. So naively, one would say that what is concurrent deformations? Concurrent deformation should just be described by the variation of the actions respective parameters is given by I, J1, wedge J2. Right? So the variations of the actions as a deformation parameters should be the same as should be the same as the current operators. But this is not enough because we know that the current operators themselves are functions of lambda, so it depends on lambdas. So the better way to do it is that we want to keep track of not just the action itself, but the actions when it couples to background gauge flows. Okay, because if we have the actions that couple to background gauge flows, then we can extract the current for free by taking derivative respect of these actions respect to the gauge flows. Okay. So now let's formulate the concurrent deformation as following. So it's not just a flow equation for the potential for the actions itself, is now a full equation for the generalized actions when it's coupled to some background gauge fields. Okay, so I demand that this generalized actions as a function of lambda, when we look at this variations, it's given by this equation, which is a very natural generalizations of what I have written already. So we see that so this is basically just a current operators with a turn on, and then we demand that the actions when a turn on, its variation is given by just the current operators at every a. Okay, so this is the way I would like to formulate current deformations more abstractly. So now, if we look at this, this can be translated into an equation for partition functions. Then this tells us that the partition function, when we look at this variation with respect to lambda, is given by this. So this is just derivative respect to A2 and derivative respect to A1. So we just take the wedge products of them when they act on the partition function. Okay, and this is how the partition functions should transform as a function of lambda. So this is the equation we like to solve. And it turns out that this solution has a very nice solutions, which is given by kernel representations. So what is the solution? The solution is given by this. Let me finish writing and then I'll explain what I will unpack the formulas. Okay. So let me unpack the formula now. So then this kernel representation is saying that the new partition functions with the background turn-ons at deformation parameter lambda is related to the original partition functions by integrating the original partition functions against the kernel. Okay, so here we path integrate over little b. Little b is where the gauge field is supposed to be sitting at for the original partition functions. And the kernel for this that appears here depends on both the background gauge fields A and this little b that we integrate over, which is given by this form. So for people who have thought about TD bar deformations, this is very much similar to the things that has appeared in TD bar deformations. Okay.
Is the B flat here, or
Sorry, can I say?
is B flat?
I'll come back to that. Give me a second. I'll come back to that.
Just Fourier transform.
This is like a diffusion equation. This equation is like a diffusion equation.
I know, but I mean, I'm just saying it's integral over B, B is just like Fourier transforming thing.
B is like yeah, but there's also B1 wedge B2.
It's fine.
Yeah, which is important. Yeah, yeah. It's basically just like
This is like Schrödinger equation where DDA is the gradient and you're going to Fourier space to solve.
that's right. Yeah, that's right. Yeah, that's right. Yeah, that's right. Yeah, you're absolutely correct. Yeah, that's right. Oh, I see. I see what you're saying. Yeah, that's right. I'm just going to Fourier space. You're correct. I'm solving differential equation. Sorry, like diffusion equations in Fourier space. Okay, so now let me make a few comments. So one comment is that this A is a background gauge field. So it has a gauge symmetry on its own, a background gauge symmetry on its own. Okay. But this little b, even though it's sitting at a place where this A sitting at, it's actually not a gauge field. So this is R value is 1 from field. And let me emphasize that this is a field, there is no gauge transformation like this. So okay, so this is not there. So this is a R value 1 from field without any gauge transformations. And the reason why there's no gauge transformations is because the kernel explicitly break the gauge transformations. If you try to perform shift B1 by some D of betas, this is not invariant. So that's why this is an R value of 1 from field, which is very important for what I'm going to say next. And there's some consistency check you might want to check is that when we take lambda to be 0, this kernel just becomes the delta functions. So if you plug it back, you just recover the original partition function. So it gives you the correct initial condition. And the second thing says that this kernel can be composed. So you can the kernels at lambda 1 plus lambda 2 are related to the kernel at lambda 1 times lambda 2 integrating against some b. Okay. So there's an equation like this you can write down. So this is just to tell you that this kernel works in a nice way. It agrees with our intuitions that we give you the right initial conditions, they can be composed. Okay. So now I'm going to explain to you why this can be understood as a topological gauging. And also let me make the comments. So this kernel with a turnoff has already appeared in Dubovsky, Negro, and Massimo's paper. In that paper, they already make a point that this should be related to current deformations. But here I gave a sort of a 3-line derivations of why this is the correct kernel. So now let's try to reformulate this in terms of topological gauging. So the way to do that is that this B, they themselves are one-form fields, so they are not gauge fields. So let's try to repackage them into gauge fields. So by introducing a Stockenberg field. So let me decompose little b into a gauge field plus a Stockenberg field. Okay. So then if I do this decompositions, then automatically I have the gauge symmetry. And okay, and let me emphasize that this is an R-valued gauge symmetry because I'm dealing with R-valued gauge fields. Okay, oh sorry, gauge symmetry. Okay. So we can always gauge fix phi to be 0, so then we just recover it back to the same equations. And here, let me explain my notation also. I use little b to represent some field that has no gauge symmetries, and capital B to represent some fields that has gauge symmetry, just like what happens in capital A. So now let me, there's another thing we need to be careful about is that I'm not doing gauge transformation, but my partition function that we start with may not be invariant under gauge transformations because there could be anomalies. So my partition functions, if I try to shift, if I replace the little b by these things, then this is the partition function I get. But this is like doing a gauge transformations. So this may not be the same as the original partition function because of anomaly. But in general, the anomaly will take the form like this, that if we do a gauge transformations, it's given by a phase factor that is given by I to the I over 2 pi KAB BA wash d phi d. Okay. So this is what happens if we can always add the right counter terms to bring it into a form like this. So then in this case, the new partition functions, now we'll just turn off the background gauge fields, are related to the original partition function now by path integral over the gauge fields. The scalar, and then I'm now so I'm replacing these things by this, okay? Then, and there's a kernel that comes out, which comes from this part. And then there's a term that's given by. Okay. So this KAB terms is just coming from the anomalies, and then this epsilon AB is just coming from this part. If we substitute this to here, okay. So this is what I get. So there's an integral over phi and integral over b. But now you see what's nice is that if I integrate out phi, so the equation of motion, we can integrate out phi because it appears linearly. So the equation of motion of phi will tell us that dB equals to 0. Okay. So now it means that if we just look at this part, we're just summing over flat connections of B. Okay. So which make it into a topological manipulations.
R value though.
Yeah, that's correct. Yeah. So let me emphasize that this just topological gauging of R times R one form symmetry. I'm coming back to the global structure in a moment. Okay. And then you can ask, what is the meaning of this part? So this is something parameterized by lambda in a continuous way. So usually, and this depends on both B1 and B2. So usually what happens is that if you have a discrete symmetries, you can gauge that, you can do a discrete overfold, and then you have choices. And choices is given by the discrete torsions. But now what happens is that we're trying to gauge R times R symmetries. So there are again choices to be made, and this choices is now parameterized by the continuous parameters. So this is basically a generalization of discrete torsions, but now it's a continuous torsion. Okay. So here we can see the existence of manifolds from the following perspective. So we have some symmetries, which is in this case generated by U1 times U1 currents. And then we just gauge that symmetries, but pretended as R times R symmetries. And when we gauge that, we allow to add some discrete torsions. So different types of discrete torsions give you different theories. And then they are naturally connected because lambda is the continuous parameters. So this is a way to understand the existence of conformal manifolds from the existence of discontinuous torsions. Okay. So
Is there like for a particular value of lambda, couldn't the thing in front of B d5 vanish or something, or like certain?
that's a very, very good question. So I'm coming back to that later. Yeah. But I think I don't have much time. So I'll make a comment about that very quickly. Good. So just to give you more intuitions of how the partition function look like, let's just consider torus partition function. Okay. So what is torus partition function doing? So let's talk about Z lambda. So Z lambda should be given by, so let me represent the torus partition functions of the original theory with the background turned on by these pictures. So this is just torus, where things are identified this way. So these things is basically just something, a torus partition function of the original theories with the background turned on. So then we can turn on the backgrounds B1, B2 in both X directions and Y directions. Because I'm dealing with flat connections, so the only interesting information are just in the holonomy. So these things will be given by insertions of symmetry defects in which generates a holonomy in the X directions and Y directions. Sorry, Y directions. Okay. So this is what happens. So this is just a pictorial way or cartoon way to represent the partition functions with the background turned on. So then what we need to do is that because we're dealing with flat connections, so the only interesting things are just holonomies, which are parameterized by this lambda. So we now just need to do an integral, not a path integral over B1x and y, and integral of B2 x and y. From minus infinity to positive infinity, because we're dealing with R gauge trace. Okay, so this is how we think about the torus partition functions of the deformed theories. So this is just a finite integral.
Does it actually converge? I don't understand.
Yeah, this actually so this might converge and might not converge. So in some cases it doesn't converge, and it depends on lambda. It depends on lambda. So for generic lambda, it converge if it's always a compact CFT. But then there are points it doesn't converge. I'm coming back to that later. It's related to the question that was asked here. Yeah. So
So it's a very basic and naive question, but in that Z lambda, you turned off the background A. Yeah.
yes. Yeah, turn off A. Okay.
That was there, but like in your.
Oh, here I already turned off A. So here I'm turning off
So
A.
what if you turn on A? Like,
Oh, turn on A, it's the same thing. So you just have you can keep putting minus A back. Then what happens is that you will see that with this B, there's you basically shift this B by A, basically. Yeah, you basically shift B by A. Yeah. But I'm just turn that off now for simplicity. Okay, so now let me, I don't have much time, so let me make a few conceptual comments. So first of all, let's talk about global point now. So it's possible that the symmetry can be U1 times U1, or U1 times R, or R times R, and things like this. Let me just focus on the simplest case, U1 times U1, okay? So when a global form of symmetry is U1 times U1, you can ask what happened here. So I'm doing an R times R gauging, but the actual symmetry is U1 times U1. So what am I doing here? So what I'm doing is the following. So when I look at U1 times U1 symmetries, there could be anomaly. And anomalies are parameterized by some you can think of it as an anomaly theory, so SPT in 2+1 dimensions. Okay, so in a 1 dimension higher pictures. Okay. So but now what I'm doing there is that even though the symmetry is U1 times U1, but I pretend that this is R times R. So I just pretend this is R times R. And then I can try to gauge the symmetry. But then when I pretend this is R times R, what happens is that the anomaly actually gets trivialized. So the way to think about this when anomaly gets trivialized is the point. So because I'm dealing with flat connections, so all the gauge fields has 0 field strength. Furthermore, because I'm dealing with R gauge fields, so all this gauge fields has 0 flux as well. So that makes this SPT trivializes. Okay. So this is related to some stories about that people might have heard about, is that if you have some symmetry that has anomalies, you can trivialize the anomalies by extending the symmetry. So this is exactly what I'm doing here. So I'm starting with the U1 times U1 symmetries, but I pretend this is R times R, and I can do that topological gaugings, and that gives us the new theorems. Okay, so I don't have much time. So let me now just give you a summary of what's happened. What happens if there's anomaly and without anomaly? So let's first talk about. Now I'm going to focus on just U1 times U1 case. So let's first talk about a case where the theory is anomaly free. So when the theory is anomaly free, it just means that the partition function should be invariant under the background gauge transformations. Okay. So since the theory is invariant under background gauge transformations, then because I'm dealing with U1 times U1 symmetries, so I can consider large gauge transformations. Okay. But large gauge transformations just means that I allow my gauge fields phi to ones. But when my gauge fields phi ones, what it means is that I'm shifting the holonomy, this for example B1x, by 2 pi times some integers. Okay. So since the partition function is invariant under the shift of the holonomy by 2 pi times integer, then what we can do here is that we can first sum over those integer things first. So this part doesn't depend on the integer components. Then when we sum over integers, it will just localize this. For example, if I sum over integer of B1, it will localize this B2 to be lambda times some integers. Okay. So this means that in this formula, even though we're dealing with R times R gaugings, we can localize the integral into a finite integrals. So for irrational lambda, if we first sum over those discrete integer components of B1x, what happens is that it will localize B2 into lambda times some integer gauge fields. Okay, so that means that even though I'm dealing with R times R gauging, I'm actually reducing the R times R gauging into a U1 times Z gauging. So this Z is just saying that B2 becomes some discrete numbers parameterized by Z. And the U1 is just saying that because I'm summing over the integer part already. So the remaining integral of B1 will just be running from 0 to 2 pi. So that's why you make it into U1. Okay. So for rational R, for rational lambda, suppose the rational lambda can be written as 2 pi m divided by n with m and n co-prime. Then what happens is that you can further reduce this down to a Zn times Zn gauging, where this n is precisely this n. And then you can ask, where does the information of m go? The information m actually goes into this part. So this part will now becomes a discrete torsion of Zn. So when we gauge the Zn times Zn symmetries, there are n choices of discrete torsions. So this little m are basically labeled the different discrete torsions. So m labeling the discrete torsions. Okay. So this is what happens. So even though we are doing an R times R gauging, but eventually the formulas can be localized into a discrete gaugings at the rational points. And this actually have very nice consequences, is that let's just take n to be 1. Okay. So when we take n to be 1, what happens is that we're setting the parameter lambda to be 2 pi times some integers. But I'm saying that the way to think about this partition functions is just basically gauging a Z1 times a Z1 subgroup of U1 times U1 symmetries. But a Z1 subgroup is nothing. So that means that I'm not gauging anything. So that means that the partition functions, when lambda equals to 2 pi m, is actually the same as the partition functions that I start with. But lambda is parameterizing the directions or parameterizing this current informations. So this is telling me that I have a conformal manifold, but this conformal manifold is essentially a circle. So if I increase lambda from 0 to 2 pi, I'm just coming back to itself. So the anomaly free case means that the theory is actually going through a circle on the conformal manifold. Okay, so you can ask, how can this happen? This happens, for example, one example, intuitive example is that let's consider C equals to 2 compact boson. So C equals to 2 compact bosons. Remember, there's a B field, and the B field actually is 2 pi periodic. So if you start with the C equals to 2 compact bosons, you can generate the B field from the theory without B field using the 2 winding currents, and these 2 winding currents are anomaly free. And then here, indeed, we see that the parameter that parameterizes this current information is B, which is a 2 pi periodic scalars, which agrees with what I said here. Okay, so anomaly free case means that the theory is going through a circle, and I think I'm running over time. Can I get the extra 3 minutes or yeah? And then I can also explain the things that Theo asked. Okay, and also non-compactness. Good. So this is what happens in anomaly free case. So let's now talk about what happens in anomalous case. So let's say when the theory has anomaly. So when the theory has anomaly, the partition function we start with will not be gauge invariant anymore. So when we do a gauge transformations, the theory might have additional phase that comes out. So let me just pick that additional. Let me just consider a case when there's a mixed anomaly for now. Okay. So this additional phase will be given by functions of B1 and B2. Okay, so it's given by B1 and phi 2. Okay. So this is what happens if we do a gauge transformation if there's an anomaly. So this is, I'm assuming there's a mixed anomaly in this particular form. So now what happens is that as Theo already asked, or Jenny asked, is that these things can now be 0. So that means that I'm at some special points, I'm not imposing the flatness condition correctly. So what are those points? So in this particular case, what happens is that when lambda equals to 0 or plus and minus infinity, the flatness condition is not imposed. Okay, so flatness condition is not imposed correctly. So at those points, we cannot interpret the theory as doing topological gauging. But it turns out that this point actually has a very nice physical meaning. This point actually turns out to be related to the infinite distance point on the conformal manifold. Okay, so the infinite distance points on conformal manifolds are the points where the theory becomes non-compact. So that means that the partition functions, if we start with the compact CFTs, the partition function actually diverges or it becomes ill-defined at this very particular point. But if we stay away from this particular point, the theory is actually well-defined. Okay, so let me explain sort of the logic behind this infinite distance. Why this theory is believing at infinite distance. So the logic is the following. So as what happens here, so we can sum over B1, or we can do the same thing as before. We decompose the gauge fields into some integer piece and some U1 piece. So let's first sum over B1, sum over an integer piece of B1. So if we do that, we just localize B2 into lambda times N2. So the R times R gauging becomes U1 times Z gauging. So this step still go through. But now the subtle things is in this step. So in this step, what happens is that if I try to decompose B2 into some integer piece as well, then what happens is that this integer piece is about doing a large gauge transformations. So, but the partition function is not invariant under gauge transformations. So that means that we will get additional phase factors if we want to do this sum. Okay, and that additional phase factors will modify this part. So eventually, what happens is that we are now not gauging a Zn times Zn subgroup. We are now gauging a Zn times Zn minus m subgroup. Okay. So we are gauging a Zn and Zn minus m subgroup, and this minus m comes precisely because of this anomaly. Okay. And now we actually have the information of M. So we don't need to use, there's no relation between discrete torsions and M now. So M just enters into this gauge group that we are gauging. So one thing that's interesting is that in this series, we have U1 times U1 symmetries that have a mixed anomaly. But a mixed anomaly can actually get trivialized if we try to gauge this Zn and Zn minus M subgroup. Because this two N and N minus M are co-prime, and one can check that when this group are co-primes, there's no way they can have a mixed anomaly. So this is actually an anomaly-free subgroup we can gauge. So the claim is that when there's anomalies, the theory actually becomes the topological aging actually reduces to a discrete gauging of Zn and Zn minus M subgroup. And this now again have interesting consequences. So let's talk about what happens when lambda equals to 2 pi. Okay. So when lambda equals to 2 pi, you can think about it as approaching lambda equals to 2 pi using this rational series, rational numbers. So you just take lambda equals to 2, you set M to be the same as M minus 1. Okay, so then this one becomes 2 pi minus 2 pi over M. So we can set, when we set M to be M minus 1, and then when we take N to be very, very large, then we are approaching that this lambda equals to 2 pi. So if we take M to be M minus 1, what happens here is that we're now just gauging a Z1 subgroup. So we're not doing anything here. We're just gauging a Zn subgroup now. So this is not doing anything. We're just gauging a Zn subgroup of the U1 times U1 symmetry. And then we take N to be larger and larger. So what happens is that when we approach lambda equals to 2 pi, we're gauging a subgroup in U1 that are bigger and bigger. Okay. And when we're gauging a discrete subgroup, what happens is that we'll introduce twisted sector operators, which are coming from the endpoints of the topological lines. And these topological lines are now labeled by exponential 2 pi divided by N times some integers. And when N becomes larger and larger, you get more and more operators coming from the twisted sectors. And because we expect the scaling dimensions, the ground states of the twisted sectors should be a continuous functions around a very small twist. So that means that we'll get a continuous tower of states coming from the twisted sectors. And now we can use the result by Hiroshi and Ifan, then this guarantees that the theory is at infinite distance point. So does it make sense? I think I'm walking through this very quickly. So the alpha is that when we try to approach that point, we are gauging more and more discrete subgroup of U1, and we're getting more and more operators from twisted sectors. And these operators will now have a finer and finer gap in their scaling dimensions. Then we can use the results by Hiroshi and Ifan that shows that the theory is at infinite distance. So one can check, let me just end by saying that one can check this in the case of compact bosons. So in the case of compact bosons, we indeed have two symmetries, which is the U1 momentum symmetry and U1 winding symmetries, and they have this particular mixed anomaly. And in that case, when we do a deformations, the radius will change as a nonlinear function of lambda, which is given by 2 pi r divided by 2 pi minus lambda. So when we take lambda approaching 2 pi, we're just going to the infinite radius limit of compact bosons, which is indeed at infinite distance. Okay. So here we see that this point where the finite conditions are not imposed are tied with infinite distance and also tied with the points where the partition functions become zero defined. So let me just conclude with that. Thanks.
Like just a technical question, I guess, in this argument. What phi is not, it's real valued, isn't it? Why are you saying that phi can wind? Yeah.
Oh, that's a very good question. So here phi is real valued. Okay. So that when it's real valued, then it will reduces you to a flat connections of r times r. So here we have integral of minus infinity to positive infinity.
Right.
Then we just decompose it into integral of 0 to 2 pi.
Okay.
And sum of integers.
Okay.
Yeah. That's more. Yeah.
Is there an intrinsic definition of distance as a function of lambda, which will help us go in the other direction?
That's a very, very good question. So that's something I wish to understand at this moment now. So you can ask, is some logical metric on the conformal manifolds naturally written in this lambda? one natural guess is that you might say that homological matrix is just given by d lambda squared. This is a natural guess, but it's incorrect. As you can see from this particular in this example, the homological metric on compact boson is given by this, something like this, which is not given by d lambda. So that's something I wish to understand a bit better, how to relate the homological metric to this d lambda. And then there's actually some nice things you can do, because there was some work that discussed averaging over conformal manifolds. And now there's a hope that if you can relate the homological metric with lambdas, then you can do an averaging over generic conformal manifold generated by current deformations. And that might be a universal, a stronger statement than what people have made about, for example, averaging over their SCFT. That's interesting.
So even though when you reach the point where this current is available to non-vertical symmetries, I still use this R values background gauge field and manipulate the partition.
So in this case, no. Okay. So let me say two things. Okay. So one thing is that you can ask what happens on a compact boson case. On the whole compact boson branch, you always have U1 times U1 symmetries. So you just use that two U1 symmetries to do the current deformation. But you can ask what happens on orthofold branch. You don't have the U1 times U1 symmetry anymore. But what is the marginal deformations? So the marginal deformation, it turns out, is also related to current deformations. So the way to understand this following. So on the orthofold branch, you have some currents which are now attached by a Z2 line. Okay. So because the currents are something like partial phi, for example. So they are charge on the charge conjugations. So they are not gauge invariant, so they are attached with a Z2 line. So these things will generate the cosine line. Some of you might know that it generates the cosine line. So this is the currents now is defect operators, but using a defect operator, you can still generate non-invariable continuous symmetries. And this is related to what's called the cosine line. And now using this operators and another operator, you can combine it. So the two operators, even though each of them are in twisted sectors, their combinations is now local operators. So then you use that to do the deformation.
Sorry, the examples that you discussed were mostly for integral theories, right? Is that correct?
What do you mean by
The
integral
examples like the Westmania models and the compact boson. Like, so the procedure, but the procedure that we described seems more general. Is that an example where you can generate conformal manifold for a theory that's not?
Maybe I don't understand what you mean by integrable in this particular context. Because it's a CFT, it's usually integrability applies to massive case, like to S matrix. You're thinking about
non-rational.
maybe you mean okay. If you mean non-rational, then that's right. It can be applied to non-rational.
Yeah,
that's right. Like for example, compact boson, like generic radius is non-rational. It's not rational. You don't have chiral. Yeah, you don't get the enhanced chiral. But let me make a quick comment about integrability since you mentioned it. So it's known that current deformation should preserve integrability, and the fact that it preserves integrability follows automatically that this is a topological manipulation. So integrability usually means that the theory has infinite number of conserved charges, but since you're doing topological manipulations, so those conserved charges will remain the same, sort of like remains hidden somewhere. So that's why integrability is preserved by current deformation. Yeah.
Massive theory.
Massive theory.
It's just some drastic failures.
That's right. It just draws the S matrix by some phase. So depends on the charge. That's right.
Maybe I can ask a quick question. Do you have a criteria of or conditions when this deformation has a T duality when it does not?
Oh, that's a very good question. Yeah. So T duality. Yeah. So if you have a symmetry that permutes the two symmetries, then they can give you T duality on the conformal manifolds. Yeah, so like for example, let's talk about compact boson. Okay. So compact boson, if you at SU2 level 1 points, you have a symmetry that exchange the U1 symmetries. It's like because T duality is SU2 level 1.
Oh, I see. You won't go to SU2 level 1 view as a global symmetry.
That's right. Yeah. So if you have a global symmetry that exchange the two symmetries, then those things generically becomes T dualities on this conformal manifold. It's a good.
In principle, the conformal manifold can have more dimensions, meaning other information direction. This is just one, like going along one direction.
That's right, and you're asking a very good question. So here I'm just talking about the case when the theory has U1 times U1 symmetries. But like for example, if you're in an SymTFT, the space of conformal filter is huge, right? Like because you have multiple U1 currents. So then you should be able to build all those currents, sorry, all those directions using. You should be able to build a whole conformal manifold using all those currents. And then there's actually something I didn't have the time to mention is that you can understand the existence of this conformal manifolds by looking at some topological defects or boundary conditions of the U1 times U1 SymTFTs. So one of the hope that I'm having now is that suppose you give me a series that have some continuous Lie group symmetries, okay? SUN or U1 to some powers, then you just study the space of defects, topological defects or boundary conditions in that SymTFTs, then that should tell you information about the space of conformal manifolds. And it's a subset of conformal, a subspace of conformal manifolds. This theory will be living. Does it make sense?
I want to know the connection between this conformal manifold and the conformal.
Oh yeah, I can tell that. Yeah, I guess that's straight. Yeah, I can tell there's some connection.
Let's think about that.
Thanks.